Assalamu alaikum students, and welcome to the lecture number 7 of Advanced Nanomarketing. Today's topic is similar to our course because now we are going slowly into the topics of Advanced Nanomarketing, and we will actually we will revise in this lecture all the 6 online lectures. I think it's difficult for you to understand this advanced nanomagnetism lectures via online lectures because it's difficult. However, in this lecture we will revise all the six lectures given in last 3 weeks. So we have discussed the magnetic relaxation in the single domain nanoparticles. So in our system, the most important is the Neel relaxation model. In the Neel relaxation model, the individual spins of the nanoparticle consist of uniaxial anisotropy and strongly coupled to each other, and EA is the anisotropy of the energy. If anisotropy energy is greater than the thermal energy, we are in a block state, and these atomic spin change their orientation in the synchronous order with the magnetization is reversed. This is called coherent rotation. We already discussed it. The characteristic time of the thermal fluctuations is governed by the Arrhenius exponential law, which is actually gives us the Neel time. Time E is the anisotropy and KBT is the thermal energy. So it's a competition between the anisotropy energy, which is the characteristics of the material nanoparticles, and it depends upon the effective anisotropy constant of the system, which includes the shape anisotropy, surface anisotropy, the core anisotropy, and the stress anisotropy. There for anisotropy we already discussed in the face-to-face lectures, and it also depends upon the volume of the system, this anisotropy barrier. So the KBT is the applied thermal energy, applied temperature. The Neel relaxation is prevalent in small nanoparticle and exists in the front state of the colloids where particles are unable to rotate physically. So Brownian relaxation gives hints when the particles are present in some dispersed in some liquid and are in the form of suspended colloids, such as the magnetic liquid is known as the ferrofluids. In this case, the whole nanoparticle physically rotate as a whole with the characteristics relaxation time given by the Brown relaxation time, which depends upon the average hydrodynamic volume of the particle and also the viscosity of the liquid. So its rotation time depends upon these two factors mainly. In the magnetic liquid ferrofluid, it is possible that the both mechanisms can be present. So the effective characteristic time can be written in the form of this equation. So we have also discussed about the superparamagnetism. Is the type of magnetism appears in a very small ferromagnetic nanoparticles. If we reduce the size of these nanoparticles, there is a limit, critical diameter below which the nanoparticles cannot sustain its ferromagnetic huge core cannot fix in some certain direction, and it can easily move. However, if we can reduce the temperature, we can block it. So with the rise of the temperature, the state also becomes the superparamagnetic. So it's a competition between the thermal energy and the anisotropy energy. So in the superparamagnetic region, the thermal energy is dominant, and then anisotropy energy in the system in the superparamagnetic state and behaves like a paramagnetic. And below TB, we are in the block state, and so anisotropy energy is dominant. So you can see in the superparamagnetic states how the magnetism of the nanoparticle is flipping, and in the block state it's in some certain direction. So at a certain temperature, which is called blocking temperature, both energy are equal, which can be found by this Neel Arrhenius equation. The TB is equal to K effective V over 25 kV. So kV is the constant. K effective is the property of the material, nanoparticles, and V is the volume of the particles. So TB changes with the volume. So if we have large particles, we have a high TB, and if we have small particles, we have a small TB. So an effective anisotropy is also changes with the TB and is directly proportion. The blocking temperature depends upon these factors. In superparamagnetic state, material have just like paramagnetic material, is except the magnetic spin single domain is much large compared to atomic spin. So TB. So superparamagnetic state can be easily understood if we can understand this curve. And the coercivity diminishes in the superparamagnetic state because the spin is fluctuating very much. In the block state, we have a system block in one well. You can look by this arrow. So in the single domain region, these two states are very important, and in the superparamagnetic state, we cannot use these particles for data storage. If you want to use smaller particles for the data storage, you must have TB above room temperature. So from the zero field cooled magnesium of megamite nanoparticles, you can see above TB we have a fluctuation of superparamagnetic nanoparticles, and below TB we are in a block state, and above TC is paramagnetic state. So here are the MH loops in different magnetic states. You can see the hint for the superparamagnetic state is the S-like non-linear behavior of the material with a diminishing with no coercivity. For the block state, we have a similar MH loop for the ferromagnetic system, and at above TC we have a typical paramagnetic hysteresis loop. From just taking the hysteresis loop at different temperatures, you can see the behavior of the system changing with temperature. So superparamagnetic to paramagnetic state is usually occur above TC. So in the coming lectures, we will also talk about the spin glass system. So what is a spin glass system? It's a disordered frustrated spin system. It's like a ordinary glass, but here the spins are randomly oriented with frustration and disorderness. In the in the glass, we have atoms are frustrated and disordered in state. So in the spin glass systems, we can observe in the bulk material when we dope some magnetic ions in the some non-magnetic material. We can also find the spin glass in the nanoparticles, which is composed of two behaviors: surface spin glass and the super spin glass. Super spin glass is actually due to the randomness between the nanoparticles, among the nanoparticles, frustrated dipolar magnetic interactions, and the surface spin glass occurs at the surface of the individual nanoparticles, where the disorder and frustration is present on the surface of the nanoparticles. So in the future coming lectures, we will discuss about these spin glass systems in the nanoparticles and nanosystems. So applications of the magnetic nanosystems is the superparamagnetic acts as a limitation for the data storage. So however, we have a biomedical application so much. In the detection, we are using these nanoparticles. In the separation facilities, in the treatment, we are using this like a targeted drug delivery. We can use these nanoparticles, and we can coat these nanoparticles with some certain drugs and target them to some certain defected tissues and deliver the drug there. So in magnetic sensors, we are using them. In ferrofluids, we are using them, and also self-assembling is also important for some different devices. So there are some references, and also your text book is important. So I hope you have understood and motivated well to read more literature from the research papers. Enough.